Hello, testing. Everyone see the screen? Is it okay? Without turning on the light. Okay, all good. All right. So welcome to general topology. Good afternoon to everyone. So my name is Seng. Okay, my last name is Seng. Feel free to call me Seng. Okay, this is your privilege. Call me Seng. Okay. Um. So maybe I talk a little bit about my background, okay, before we start, so that you know why I do this, why I said this, why I said that. So, so this is a pure maths class. Everyone agree? Okay, so this is a pure maths class. Um, so most probably you are on the pure maths path already, right? Okay. So I was taking pure maths in Australia. Okay, I've done my bachelor degree in Australia for 4 years, and then we bachelor with honors. So we have a thesis to write. Somehow similar to the honors here, but the time you took for honors here is just 3 years, right? Okay, so there's difference of 1 year, which is quite a large difference because in 1 year you can learn a lot of stuff. Okay, so with these honors thesis, I go straight to PhD in Seng University, ANU, okay, in Canberra. What I did is in the area of representation theory or higher representation theory. It's about category theory. So we're trying to study modules. Have you guys heard about modules? It's like a vector space over a ring instead of a field. And we're trying to link modules with topology together. In particular, we study topology of a punctured disk. So imagine you have a disk, okay, and then you punctured it. Um, so that topology and this topology is a little bit different. Okay. The topology we will study here is called the point set topology. So we study a set and then what are the elements there? What are points there? Can we define a distance between any 2 points? This is our main problem in this course. Okay. And you can imagine what kind of set you have. You have a set. Inside that you have elements. You can count elements, right? Okay. Maybe there are finitely many elements there. For example, in this class, how many students here? 1, 2, 3, 4, 5, 6, 7, 8, 7. So there's 13 elements in this set, for example. And between every two elements here, there's a distance, right? You can find empty space between two elements here. But can you do it for an infinite set or not? Okay, imagine you have a crowd, right? You have a crowd. Can you observe that in a crowd, the distance between two objects decreases if you have the same space, for example, right? For example, inside this room. Let's say I put 100 of people here, 1,000 of people here. Does the distance decrease or not? Okay. If I increase more and more and more and more, make you into a sardines, like a sardine. Can you still differentiate 2 points or not? Okay. Yeah, this is what about a point set topology. So since this is a pure maths course, right? Pure maths can get really hard, really abstract. Okay, so what I want you to do is you should get some help from your friends here or get help from me. Okay, you have to ask for help. Otherwise, we cannot help you, okay, if you don't speak up. Okay. Okay. So you have heard that a lot of people like study pure maths and then they what? Any myth or not? You heard? No myth. Got myth? Okay, if no myth, then that's okay. I don't want to introduce myth. But try to get help. Okay, try to get help. So in this class, I want to experiment something. So I want to get two class representatives here. Anyone want to volunteer to be a class representative. So what does this class representative do? So this class representative, you can give feedback to them. Okay, you can give feedback to them, and they will feedback to me if you don't want to talk to me directly. Sometimes you will feel that. Also, this class representative can make a study group. Okay, can make study group among yourself. And one thing you could try is you can get me to visit your study group. So maybe it's like a tuition like that. Could be. Okay, if my time match with your time, maybe I can go and see can solve your problems or not. Right? Does it make sense? Does it make sense? Yeah. Anyone want to be a class representative? Anyone? So yeah, group. Okay, how about this group? So I prefer we open the group in Teams. Okay, so we can take less formal, informal, casual talk about this class, content about this class, or how to say, the well-being when you take this class. Yeah, it's not completely casual, but less formal than emailing me or what. You can. Okay, so we will have Brian. Okay, can I have another one? You, Gary. Okay, okay, sure. Okay, good, good. So we have a Gary and a Brian. So after this class, you can try and get contact here. Okay, and open up the group. So there will be, I think, 13 of them here. So if there's newcomers, then we will add later. But just add those here first. Okay. So it's a class team group chat. So so what else I want to talk about? Okay, let's talk about the structure of this course first. Have you guys enrolled in the Moodle yet? I know one of you haven't, right? Please email me. So I need to know your identity. So wait. So where is it? Okay. So if you go to the Moodle, go here. Okay. So first, oh, I put the wrong name here. Okay, never mind. So I put wrong name here. Then later I'll fix it. I'll put Brian and Gary here. Okay. So how to find me, right? Based on appointment, Tuesday 3 to 5, Thursday 2 to 4. Any clashes with your schedule? No? Can you make it to any of this time? Tuesday 3 to 5 or Thursday 2 to 4. Can you guys make to any of them? So on appointment, if you want to kind of find me, you make appointment first. I don't want just wait there and then no one come. Okay, so far so good. All right. Next, most important thing, the material we use is here. So we are based on 2 books here. One is by Richmond and the other is by Mark Chris. Okay, based on these 2 books. So after I lecture, if you understand what I say, go back and read the relevant topics. And I will put pre-reads every week. Okay, before you come, it's better you go and read some of the relevant chapter first, and then you come and listen to lecture. Otherwise, you will easily get lost in the lecture. Okay, please do this pre-reads before you come to the lecture. And when you come to lecture, okay, so I should tell you what's the setup of my lecture. So let's go to this course info. So my class structure is like lectorial style. So it's a lecture plus tutorial. Okay, lectorial. So why I ask you go back and study first and then you can't? Because you can bring your question here, okay, and ask me on the spot. And then we can discuss. Maybe the student will say, oh, aren't we interrupting you? Yes, you are interrupting me. But at the same time, you are also helping the others. okay? Because others will have similar problem. So we could solve it in the class. Or if I cannot solve it, then I will go back and solve it and then we discuss again. So the principle is you have problem, we solve it in this class. Okay. So I'm a little bit different from the other lecturers. Maybe some lecturer doesn't want to entertain your question or what, but I'm interested in ideas. Yeah, I'm interested in ideas because if we are doing pure maths, ideas are really, really important. Even stupid ideas can generate a big impact. Okay, so ideas is really important. Actually, no questions are stupid. Okay? Because just that sometimes you think of it from a different perspective. But maybe this perspective is what we don't want or what we want. If it is what we want, then maybe we can generate new stuff. Yeah, no? Does it make sense? We're trying to be open in this course, in this class, right? In my class, I always try to be open. My class value freedom because this is what the Western country education focus on. Okay, so I'm kind of a mix of Eastern and Western culture. So I will be strict sometimes, but fairly fairly free in the higher education part. Okay, in the research part. Okay, because this is how the Western do their research, how they generate new stuff, right? So this mix of education actually proven working quite well in the international level. For example, Yang Chen-Ning, you know, Yang Chen-Ning. Is it Yang Chen-Ning? Yang Chen-Ning. Yeah, Yang Chen-Ning. Chen-Ning Yang, right? Is a physicist. He got what he got? He got a Nobel Prize, right, in physics. Yang Chen-Ning, everyone know no? Yeah, Yang Chen-Ning. So he is a mixed education from Chinese and US. So he went to US to do PhD. And another example is Chen Xingsheng. So he has impact in the K theory about Chen class, Chen Xingsheng. Yeah, he is also a mixed education. He was doing a bachelor in China and then go to US to do PhD. So it's proven quite well. So far, I haven't seen anyone that graduated from purely Asian university and then did something great. I mean, great in the sense that people acknowledge it. Right. So I think we should get something out of this kind of mixture. Okay. Yeah. So one thing is please don't keep everything to yourself. Okay. Try to set up your problem and then we can try and discuss it and see if we have get some good solution. All right. Next is learning outcome for this course. Okay, so you should read about it and then what to expect here. So actually our course, right, is shared with a master. Okay, so there's a master code here, 416. So undergrad code is 0208, master is 416. So master have extra assessment. So don't be afraid with these suggested reading, okay? So these readings are trying to help you if you don't understand the two textbook. Okay, then you can go down to this list and then find any one of them that suit you. Okay. So I'm trying to reduce your job to do research. So you just go to this list. If this list doesn't suit you, you should feel free to go for other books. And I think for some of them, I have posted out the solution manual. Let me show you. Okay. Yeah, so I posted out the notes here. So first of this is the Prof Tier notes on general topology. It's quite clean. You can have a look. Sometimes I also write based on this. And the other one is notes by John Hutchinson. He's a professor, I think emeritus in NU. This is what I studied before. So I put all these for you to have a reference. And then I posted all the textbook links and files here for you to read. So you don't need to find yourself. And I also posted out, for example, solution manual to Mark Chris. Okay. So in the class, I'll try to type out weekly tutorial question for you to do, and then I will give solution. If you think that is not enough, again, you can go to Moncrief and then do the relevant exercise and their solution then. And in case you don't understand problems or solution, you can come back and ask me. Okay, we can discuss it in the class. Okay, I'm quite open to question here. The last one here I want to mention. So the last one here is by Lipschutz. Okay, this is the Scums outline series. So do you guys know about this Scums outlines book? This series of book typically have a lot of examples, proof, exercises, okay, for various topics, which is like an introductory, to the course, to the topic. Okay, so it's a very beginner introductory books to topics. You see. So the topic we are interested in, most of them are in here. So you can try their exercises because they have a solution following the exercises. Okay, and then they somehow do like summary on each topic. Okay, so Scum's outline is a very good book series. Okay, for you to study a new subject. Okay, so this is my lectures. So this is the last one. I put there plenty of examples. Okay, so please come to here. Okay, in mathematics, we don't like a thing is like getting stuck. Getting stuck is quite dangerous in mathematics. So you need to make yourself keep going on. So how to keep going on? So you need to go through different references or you go and ask people. Okay, getting stuck is not very helpful. You won't be unstuck by getting stuck. Okay. You get what I mean? You cannot unstuck by just getting stuck. Then you need to do something. Okay, you need to refer to new material, listen to new ideas. Okay, you can never unstuck by just getting stuck. Okay, you need to absorb new material. All right. So yeah, so I set out these three forums here. So first is announcement. Maybe I'll make replacement announcement, exam announcement, and so on. And I set out a student forums here. Hopefully, you can use it. Okay, you can ask questions here so that the other students can help you. And I put a key sense question time here. So you have any question you want to direct to me, you can put it here. Once you put it here, I'll try and solve it, and then I will discuss in the lecture. Okay. So this is what my previous administration, what I did to my previous class. But my previous experience is the last two columns will be empty. No one will be using it. So that's why I want to come up with this team group chat. So I want you to start with a casual chatting first. Okay. So you feel comfortable to talk with each other. So I don't know why, but I think for Asian, you guys rarely speak to each other, or you rarely want to express your view because you might think that I might get wrong, or maybe I might offend people. But this is how we learn actually. Okay, you need to test wrong. Yeah, test wrong. You need to test wrong. And this is really different when I study in Australia, right? The student could be like discussing all over the places during the tutorial. But when they do assignment, their assignment is pretty bad. But when they discuss, you think like they are talking all over the places, all over the world, everything over any subjects. But they don't do good. This is their drawback. But what we want to do here is we want to learn from people's how to say, 优点. Yes, learn from people's strength. Right. Although maybe you can do your assignment good, but can you express your idea to the others or not? Okay, try and do it here. Test wrong here instead of later. You will definitely need to talk to people when you go out. Okay, so test wrong here. Is it okay? Okay or not? Okay, so this is really important for this community to grow. Okay, otherwise you'll get really isolated, getting more isolated. Okay, so I have listed out all these references you can refer to. So our content basically split into 5 topics here. So first part is set theory. So this set theory mainly will focus on cardinality and axiom of choice, because we want to count how many things inside there. And then we want to study properties between points. And then second topic, we will talk about topological spaces and continuous functions. And here we will introduce a metric spaces, which is distance for spaces. It is a distance function for spaces. And then part 3, we'll talk about connectedness and compactness. I think connected, where's your first time seeing connected? MAT2? I thought Cal2 we already see it. I teach Cal2 twice. I mean, okay, they don't have focus on that, but that's one of the conditions for some theorem to work. But MA2 is an advanced version for Cal2, so you definitely saw it there. Okay, connectedness and compactness, and then 4 countable and separable spaces, whether points can be separated or not. 5 is a complete metric space. So complete metric space, I think you have seen one of this example already. Actually, it is real numbers. Real numbers is one of the complete metric space. Cauchy completeness. Okay, let's come to assessment. So we have different assessment for 208 and 416. So for 208, I plan to do 10 take-home assignments. So because it's a weekly, so it's gonna be shorter than like fortnightly assignment. Hopefully, I try. Okay. And there's a test 20%. There's a final exam 40%. So for master, I think we only have one here for now. Okay, Wen Chuan. So Wen Chuan will have no test. Okay, you have no test, but your test is replaced by report and presentation. And your final will be different from them as well, a little bit different. Okay, so you have a report and presentation. Let's quickly run through this report and presentation, although there's nothing to do with 208. I set a topic. I call it the marriage with topology. Okay, so what is this about? So I want you to connect topology with other topics. Okay, so for example, with differential equation, with differential geometry, number theory, mathematical physics, analysis, algebra, category theory, symplectic geometry, group theory, representation theory, knot theory, algebraic geometry, functional analysis, maybe with probability theory, stochastic, statistic, chaos theory, dynamical system. So what you do is maybe you pick one paper or what, and there's a relation between topology and different field, and then discuss about it. Okay. Details are written here. If you don't understand, maybe you can ask me later. And then you will need to do a presentation on this topic. Is it okay? Yeah. So if you like algebraic number theory, right, see whether there's topology there. Just pick one paper or what, and then discuss about it. And then see if you can figure out some open question or not on that on that combination. Yeah, I think we are quite looking forward to you. See if you can connect topology in any sense. Okay. Yeah. So far, any question on this assessment? Oh, okay. So let's come back to slide. And I think our calendar are quite busy over the next few weeks because we have a lot of holidays, right? We have a lot of holidays. So I think we should pick some holidays class. So next week we have holidays on Wednesday and Thursday. Right. So we need to replace both class. Okay. So any common times you can do for replacement? Can you check your schedule? Our course is quite a mix of the third year and the second year. So we need to figure out a common time here. Any possible time for replacement? Can everyone check your own schedule? And then sorry? Monday or free, okay? Is everyone good with Monday? It's good then we fix Monday. Then I can pick any choice of time. Just 10 to 12. Okay, just cannot 10 to 12. Okay. That's all. All other time people free on Monday. Okay. Because Monday is also another issue. A lot of holidays on Monday. Okay, so we only can replace in alternate week, I think. Any second choice of time or not? Friday. Friday whole day. Except 9 to 11. So after 11. Everyone else? 2 to 4 also cannot. So 11 to 2 and then after 4. 3 to 6 cannot. Then this one don't want. So 11 to 2. Everyone can do 11 to 2. You cannot. Oh, GG. You cannot. Okay, then never mind. Friday, then forget. Forget about Friday. No other days. Any other days you guys can do? Hmm? Wednesday. Okay, Wednesday, what time? No, you cannot. You full day, gone. Okay, Wednesday cannot, Friday cannot. So left Tuesday and Thursday. Hmm. How about Tuesday and Thursday? Tuesday morning. Before? Before 2, before 12. Before 12. Before 12. Tuesday before 12. You cannot. You full. Ah, okay, then cannot. Tuesday afternoon cannot, is it? Oh, you full. Okay, then never mind. Forget about it. Thursday, full. Okay. Okay, either we do Monday or either we do online night time. Is it possible? Online night time. Every night, okay, you guys? Not for every night, I mean, pick a choice. Pick one night from a week. Something like that. Okay, okay, sure. 6 to 8, mostly can. Okay, Tuesday cannot. Okay, the other day, okay, 6 to 8. Okay. Friday, 7 to 9, you also have class, so only left with Monday. Thursday cannot. So Monday and Wednesday, one night, if we want to do. Okay. So I will opt for physical first, and then if we cannot, we really go online. Okay. Sure. Okay, let me think what else we want to do. Okay, we set our teams. Okay, attendance. So attendance must be 80% and above. If it's less than 80%, we will bar you from the exam. So meaning you can have a 6 time freedom to skip my class without letting me know. Again, the reason. Then you have this freedom to do. But the reason that I only accept is you have to apply to AA first, get a valid uh, leave, then I will excuse you with reason. Otherwise, you were taking leave without reason. So you can only do it for 6 times maximum for this semester. Okay. Let me see what else I want to talk about. Okay, so I always show this to undergrad. Math is hard. Yeah, but with hardship, hopefully you will see the paradise at the end. Okay, so please don't give up. Okay, it will be really hard. It will get really hard because basically this course is the second hardest course when I had in my undergrad graduate. But I'm not trying to scare you. I'm more scared because I'm teaching MA1 and general topology this semester. This is even harder. This is the two hardest course I take in the undergrad because MA1, we basically did it in the first year. For the first time I see max is epsilon and delta. So you can you imagine that? And I don't know what is epsilon delta is doing until my third year. Okay. So it's normal that you can't fully appreciate this course, but please don't give up because it will make sense to you afterwards. Okay, even not now. Does it make sense? Okay, it will definitely make sense because people are already making sense of it. You know, and actually, this general topology is kind of a basic course in pure maths. If you're gonna do, if you're gonna learn more pure maths, this is really a basic course. Why is it hard? Because it's getting abstract. Okay, it's getting abstract. Okay, yeah, but it just serves as a basic course actually for pure maths. Okay, yeah. So we're gonna open. Hopefully, we're gonna open algebraic geometry in the next sem, September, and then in the coming April, hopefully we will open an algebraic topology for undergrad as well. Okay, so we will have a better lineup of pure maths subjects coming soon. Okay. All right. Let's see if I forget anything or not. Okay, anything you want to ask about the structure of the course? How do we as what do you expect from the course? Anything you want to ask? So basically, we will have a 1 hour lecture or discussion, and then we take a break, and then 1 hour take a break like that. Any question before? I think we should take a break before we start the uh, actual subject. Any question? No. Okay, if not, let's take a break until 12. So now it's 39. So let's take a break until 12:49, and then we'll start the actual set theory. Hang, huh? Okay. I'll do it now. I'll do it now. 首先，听说你 drop A2，哦，你根本没有拿，你连拿就没有拿。我要问的时候就直接。哦，是啊，你就中到了，这样 lucky 啊你！你是钉在那边是不是？你有没有钉在那边？你是第一个按进去的吗？没有诶。嗯，属于是3个。哦，你也跳了啊！我靠，OK OK，啊，什么？他很伤心，哎，你们抛弃他，他找很多人吧，做他们了，他找你又找我，嗯啊，他讲吗？你电脑会坏啊？不是那天坏了没？买新的啊，这样就那是个带电人，买新啊，怎么会坏到那样就奇怪？你是推他，人怎么会这样突出来？优秀，你优秀啊，但是等下又坏，别人修得好没？对啊，那等下又拿个路撵一下。哎，can can yes yeah. So please start some conversation there. I don't want it to become a dead group. Yeah. You can ask whether they are how they view this lecture, and then you understand what Kisen say, and then they say Kisen say it doesn't make sense. Okay, why doesn't make sense? And discuss. So if any problem that you guys cannot solve among yourself, you should come and feedback to me. Okay, and then we try to solve it. This is about research. This is about research. This is about how you go to how you do PhD. So we have problem, then we try and brainstorm it, and then we try to solve it. Okay. Yeah. So my lecture will be like center as a research style. Okay. So you're free to ask questions, free to challenge me, even. Yeah. Because I won't spoon feed you. Sorry. I won't spoon feed you. I won't tell you how to do what to do. You have to figure out what to do. But I give you the resources. I try to give you as many resources I can. But to do exercise, extra exercise, you need to put your own effort on. Right. So for this course, actually, before this course start, I already put effort in. I asked AA, don't put my class at 8. They used to put my class at 8, and then my student complain. And then they don't want to come. And then it's also hard. And then they're very sleepy, so on, so forth. So I complained to AA. I said, please don't put my class in 8 again, because it's going to be a hard course. Okay, so that's why our course is like in the middle of the day. Like that. A bit disrupting for my lunchtime, but that's okay. We need to make some sacrifice. Okay. Okay, in this case, right, maybe let me take some attendance for the day. It's Zhou Yifeng, Zhou Yifeng, Zhou Yifeng here or not? Not here, Zhou Yifeng. Cheng Xi Yuan, Cheng Xi Yuan, not here, not here. Cheng Xi Yuan, not here. Lee Peck Hong, okay, nice to meet you. Brian, okay, Brian. Pyong Yuan, yep. Gary, okay. Jian Xiang, oh, Jian Xiang. Oh, so you are Jian Xiang. Have you managed to find your supervisor already? Oh, yes. Who? Oh, Qing Hao. Okay, okay, good. Jun Jae. Lim Jun Jae. Okay. Gong Si Yu. Okay. Okay. Jing Bo. Okay. Ding Yu. Yeah. Ziqian. Sayed. Jia Yi. Is Jia Yi? Oh, Jia Yi. Okay. So you are transferred from physics? First year. First semester you already transferred. Okay, good. Um, Hang, we have Hang here, so go toilet. Yeah. Anyone I haven't called yet? Yeah, no. Is this an all male class? Is this an all male class? All male. All male class. All guys here, not female. So this is a typical mathematics class, no females one. Mathematics kind of dominated by male. So first day already have 2 absentees. Okay, never mind. Right. So should we wait for Hang to back? Come back. Let's wait another minute. If Ihan don't come back, we'll start. All right, I want to share this phrase, this paragraph with you. So I like this paragraph from one of the book in analysis. It says that the exercises are really important. Okay, you cannot just listen to concept or ideas and then you think it makes sense, but you need to make sense that it works. Okay, you need to do all exercises to help you understand more. And another thing is doing exercise, right, can train your muscle memory. Okay, meaning when you see the question, your hand can move, your hand can actually move, not your brain only. Okay, your hand can actually move with your brain together. Yeah, because I got a student says that in exam I see the question, I know how to do that, but I don't know how to write. Okay, so you need to do exercise. Okay, pretty much the same thing happens with your physical exercise. Okay, you need to do exercise, hand and the brain. So I'll try to come up with weekly tutorial questions, and then you will do it at home. And if I think it is worth to discuss, I will bring it up in the class to discuss together. Or you should ask me, okay, how to do this question or this part I don't understand or something like that. And maybe I will release solution in 1 week time, something like that. And then you can compare your solution. And you still don't understand the solution, what to do? What to do? If you don't understand the solution I post, ask who? Ask me. Ask me. Okay, don't keep it to yourself. Ask me. Whatever problems you have, come and ask. Okay, don't keep it to yourself. Because I cannot read your mind, I cannot read your mind. So you need to tell me what you want. All right, so we are done. Hey, why Jimbo go again? Okay, so in this, my lecture style is like this. So I break into this 7 part here. I colored my lecture notes so that you know what to find. Okay, if you are look for definition, you go to the white thing. If you are look for examples, you go to the green words. Okay, so this should be the lineup that when you try to study a new subject. Okay, so first part we hope I will do motivation or use questions, observations to introduce some new concept definitions. Then follow up, we will have actual definitions or axioms that we need to use. And after defining this definition, we need to make sure the definition works. Okay, so we must have working example or non-example, something that doesn't satisfy the definitions. And then we will try to deduce some properties about these definitions. So we will prove some theorems, propositions, lemmas, or corollaries, or prove some claims. Okay, so to prove them, we need to use actual proof, okay, mathematical proof, or sometimes I will just sketch the idea if it is too tedious. And how to prove? There are a few ways to prove it. So you can use direct proof, contradiction proof, contrapositive proof. Hopefully you are familiar with these things. And sometimes I will attach some homework to to those subjects. And I'll introduce notation or remarks, follow up by these definitions sometimes or theorems. Okay. Notation is really important here. Notation. When I say notation, right? Because once I introduce the notation, I'm going to use it. Okay. So pay attention to this notation. Because most of the time you don't understand the statement I say because you just don't understand what I'm using. So notation is really important here. It's not trivial. Okay. Because for example, when I talk about empty set, maybe I just put 5. Then when I talk about 5, it's just empty set. Okay. So you need to switch between symbols and words. This is what pure maths people did. Okay, we need to switch between symbols and words easily. Okay, seamlessly. Last part is maybe I have some extra comment, my own thinking, or some add-ons to the subject. Okay. Okay, so this is the setup. Okay, so I think we start the actual topic. Okay, let's start with set theory. So we won't start with propositional logic. Okay, that is what I do in MA1. So here we start with set theory. Okay, or more correctly, we start with a naive set theory. Formal set theory you need to do in other course. Actually, you can spend a course doing the set theory. It's like the foundation of mathematics. Okay, but our school not yet offer this course. Okay, so we will talk a little bit about set theory, mostly on cardinality. Okay, so let's do some motivation. Have you guys heard about Russell's paradox? Yes. Do you know what Russell paradox does? Can you explain a little bit what you know about Russell paradox? Hmm? Can or not? Cannot. Who? Who wants to say? You want to say? You don't know how to say. Anyone know how to say? Or want to say? Yeah. Okay, so what's Russell paradox? So suppose I define a set contains elements such that the element doesn't contain itself. Okay. So I claim that there's a paradox here. Okay, what kind of paradox here? So if X exists, okay, then what? Then X either in the set in itself or it is not an element in itself. Make sense or not? Does it make sense? I didn't specify where I'm going to pick the X. So X itself could be in there. Make sense? Okay, good. Makes sense. So let's try. There are two possibilities, right? Let's try. If X in X, what happened? It's not in itself. Contradiction. You have P and not P exist together. Okay, this case cannot. Okay, contradiction. The other case. If X is not in X, what happened? X is in X. Why? Because it satisfies the predicate. But you have P and not P again. Again, contradiction. So this is Russell paradox, famous Russell paradox. So what's the problem here? So what's the problem here? What's the moral of the story here? So there is no universe, a real universe that includes everything. There's no real universe. Okay, there's nothing that contains everything. Okay? So to make sense of this set, right, you should specify a proper universal set that it works, and specify the condition that could hold inside that set, whether it is true or false. Okay, cannot be both true and both false. Okay, so you need to, if you're gonna pick, so there's no real like actual universe, but if you're gonna pick some universal set, make sure the predicate makes sense. You could get empty set, but you cannot get contradictory statement. Okay, does it make sense? Okay, so because of this, right? Okay, because of this, instead of defining what is a set is, we won't define a set. So what do we do if we don't define a set? Do we do? If we don't talk about set, we don't define set. We just talk about the membership of a set. We just talk about what things is in the set, what things belong to the set. Okay, we just talk about the membership of a set. Okay, so define. We will write little s is an element of X if S is actually an element of set S, and S is not an element of X otherwise. So sometimes we can swap the order. Mind you, it makes sense to write a set contains element S. So the set X contains an element X. Okay, this is a little bit different from what you know from discrete math. Discrete math, maybe even just now when I taught MA1, we defined that a set is a collection, unordered collection of distinct objects. Okay, we tried not to define set. We just talk about what is in the set now. Okay, what thing is in the set. So similarly, we can define whether two sets are equals or not. Okay, so two sets are equal. So we denote by x equals to x. Okay, so in mathematics, I want to warn you that equality come out everywhere. So you need to make sure what's the thing beside equals. Does it equal as set, equal as number, equal as isomorphic as ring, field, and so on. Okay, so this equality is equality of set here. So they are equal if they have the same elements. Okay, so if you use membership to talk about is for every x, is in S if and only if x is in T. Okay? So sometimes in a formal set theory book, you'll see that this is actually called an axiom of extension. Okay. Actually, there's a very good classical book about this, naive set theory, is by Paul Hammers. If you can have a read. Okay. Paul Hammers, naive set theory. The title is called Naive Set Theory. Okay, so this is about equality. So in my course, right, you can don't copy everything what I say because I'm gonna post it up later. What you need to do is try and listen carefully what I say. Okay, think about whether I say makes sense or not, and then think about possible problem or questions. Okay. Next, definitions. So we will define subset. Okay, so set S is a subset of a set T. Okay, so we write it as S and then C and then horizontal line T. Okay, subset of T. If for every S, okay, S is in X is in S implies X is in T. Okay. Hopefully this refreshes your mind about this subset. How about proper subset? So set S is a proper subset, okay, of a set T if it is a subset of T and it doesn't equal to T. Okay, you need to find something in T that is not in X, S. Okay. Or sometimes, right, you will see in the literature, you will see they write S, C, and then slash out the horizontal line and then T. Doesn't equal. Okay. Another notation I use is, I haven't put my notation, or this one. Okay, I don't put the horizontal line. Usually this is what I use. Okay, so this is what I use. So let me put here. Okay. All right. So the next thing is, I think, famous. So let me see. Okay. So let me introduce a proposition. So there exists a unique set with no elements. You know what set is this? There exists a unique set with no elements. Empty set. Okay, so this is what we call the empty set. So how do you construct this set? You construct this set or not? Even the definition for our membership of set. Can you construct this set? So here there's two parts, right? The exists exclamation mark. Existence and uniqueness. So can you prove existence or not? I think we did in AA last semester, but we did it in a different way for existence because now we have changed our definition. So how do we construct an empty set now? Based on membership. Any idea? Okay, I give you some times to discuss. I give you 4 minutes. So discuss with your friends at the side or at the back, at the front. Okay, talk to them. Tell them what is your name. Okay, and then talk to them. Discuss how to construct empty set. I give you 4 minutes. X in where? Huh? All X, epsilon X, X is in X, then X is in T. So that means all X. We haven't defined You haven't defined what? Okay, let me write like this. So here is a two statement. For all X in X, X is in T, and for all X in T, so yeah, shorthand notation. It's a shorthand notation. It's a shorthand notation for the Okay, let's come back. Okay, so just now one of you asked about this notation here. So for X, S is in X, is if and only if X in T. So you are right. You need to ask where this X lies in, right? But really, this is a two statement here. So for all X in S, you have to prove that S is in T, and for all S in T, the X is in S. Okay, so this is actually a shorthand notation for this two statement here. Okay, so this is just to clarify. Okay, any ideas? Anyone want to construct the empty set? Anyone want to construct an empty set? Hmm? Anyone?
With no element.
And then? Wait. Let him say. Huh?
Suppose we have
Mm-hmm.
two sets
Mm-hmm.
S and T.
Mm-hmm.
They are not equal.
They're not equal?
Yeah.
And
then we have we prove by contradiction. We want to say that all sets that have zero elements, they are equal.
okay.
So S have no element T,
Okay.
and T have no element T.
Sure.
We assume they are not equal.
And then?
Then we can find that since we can prove that they are equal because there is no element here from above. Some extension. We find S equals to P. So all sets with no element are the same set. So we call that empty set.
Sure. I mean, this only answer about uniqueness, right? This is uniqueness. So we want to ask about existence. Does it exist or not? Actually, this is a pretty important question in mathematics. Existence and uniqueness. Something could don't exist but it's unique by property. It have to be unique, but it could just don't exist. So existence is actually very important. So can you construct one here? You mean use the Russell paradox?
For X.
So okay, tell me what's this set equals to? Can you say like this or not? Try.
Two set there's no intersection. Because two set
Uh,
intersect, there's some way it is either a set with something or nothing, but they I don't know, that's why I'm asking.
I get what you say. Sure. So you just take two things okay. You take two set with elements, but they don't have elements with common. Yeah. But we haven't introduced intersection here, so
Yeah.
you can do that. Yeah. If we introduce the intersection, you can just take two set that don't intersect together. For example, what? For example, just now I gave an example in my class. It's like Malaysian and Australian. The intersection of these two should be empty. Why? Why? Far away. No. You cannot? Why? Only one? How you define Malaysian and Australian? Do you guys know? This is by law. Citizenship. Yes, Malaysia only have one citizenship. Can they only allow one citizenship? But Australian, you can allow dual citizenship. But if you are Malaysian plus Australian, if the Malaysian government discover that, you need to renounce your Malaysian citizenship. Okay. Yeah. Think you want to continue with the argument? No? Yeah. Yes. You can try this. So S such that x not equal to x. Yeah. Yes. Okay. Yeah. You can do this. Everyone should be equal to itself, right? Or you just pick any set you like. Okay. Make sense? Does it make sense? Russell one, Russell one, there's few problems there, so we don't have a universal set for it. So maybe you try and set some universal set, and then I guess should work. You can try. Try and fix some universal set first. Okay, but in this case here, whatever set you pick, right, every element should be equal to itself. Equal in the sense of that set. You ring or what depends. Okay. Yeah. So uniqueness. Does everyone here seen uniqueness proof before? Should we do it or should we skip it? Anyone want to see uniqueness proof? Sure, huh? Okay, let's do it. Let's do it. Do it one by one, okay? So this is the start of the course. Let's not skip too many things. All right. So like what's your name? Who is beside Brian? Jia Yi, huh? Okay. So let's follow Jia Yi ideas here. So assume two set ST are empty. So let's say if they are empty or contain no elements. Okay, what do we want to show? We want to show that S equals to T. So how to show S equals to T? There are two parts we define, right? You need to show that S is a subset of T and T is a subset of, sorry, yeah, okay. S is a subset of T and then T is a subset of X. Okay. This is pretty much like numbers. You want to prove that two numbers is the same, you show that one is less than or equal to the other. Okay. All right, so let's pick one of them and show it. So let's show first, we show S is in T. It's a subset of T. So how to show this? What's the definition of subset? You still remember? Every element in X, F is in T. Okay. So that is for every element in S, implies S is in T. Hey, we want to show this, whether this statement is true or not. And of course, we want this statement to be true. How is this true? Okay, so since S is empty, right? So since, so let me write down, since S is empty, X in S is false always. There's nothing there. Okay, so meaning you have a false statement implies some statement. So the whole statement is vigorously true. Okay. So let me name this statement here. So one is vigorously true. So we have shown that S is a subset of T. Okay, so similarly, you swap the role of T and S. T is also empty, so you can use the same argument to show it. Does it make sense? Any question? So here, there's a logic trick here. So false implies everything. Yeah. Sure. Yeah, sure. you pick some sensible A and then use sensible equality here. Yeah, sure. That's right. That's right. Yeah. Or even right. Okay. Because you talk about intersection, right? We also can take difference actually. If you still remember difference, let's see if we're gonna introduce this thing or not. I think we're gonna introduce these things, but will be a little bit later. So for example, you can take intersection. Okay, you become empty, or you can take difference with yourself. A minus A. Something in A, but not in A. I think this is similar to what you guys said just now. Right? Something in A, but it's not in A. It's a contradiction. There's nothing in there. Okay. So the Russell paradox is like you need to pick a proper universal set and then you can talk about it. Okay. Yeah. So there are a few ways to get it. Okay. You can use so let me remark here. You can use intersection to get it or differences. But now we haven't introduced these two, so better don't use them first. Okay. Yeah. So mathematics is like this. If you can solve with a primitive, I mean not primitive, easier way, okay, don't involve too many machinery is better. You opt for the direct way to solve a problem, or not going through a lot of detour, come back. But this is not quite true when they solve Fermat's last theorem. They use a quite sophisticated tool to solve it, like the elliptic curve. So the question is, can you provide a simpler way to solve Fermat's last theorem or not? If you can, maybe it's another great achievement. Because for now, that's machinery is really sophisticated. It's talk about geometry stuff. But Fermat's last theorem is just about number theory. Because there is this integer solution. Wait. Okay. Yeah. All right. What's the time? Okay. We are good. So let's go on. So next. So for all set, there's not empty. Okay. Empty set is a proper subset of X. Is this obvious? Is it obvious that empty set is a subset of every set? Obvious or not? How obvious is it? Yes, still using vigorously true. Okay, there's nothing in X, but S is in S, so vigorously true. How about the other direction? Because you want to show proper, right? You want to show that they can't be equal, meaning there exists some S in the X in S that's not in here. All right, sure, you can pick some S here. Then you show that that element cannot be in the empty set because empty set has nothing. Okay. Do I write down the proof or not? Or are you guys okay? Maybe I can write it down in my written lecture notes. Okay, then you can have a check later. Okay. So proof left as an exercise, and then you could check back later. Okay, definition. So take note when I say exercise, right? Okay, exercise meaning I actually have shown you some similar working already. You just need to modify that kind of argument to get new result. That's why I will leave it as exercise. Okay. So it's not like completely new thing. You need to use some similar argument from previous proof to do it. Is it fine? Fine. Okay. Okay. All right. Next, we will define the power set. Hopefully you still remember what's the power set of a set. Well, what's the power set of a set? Yes, it's the set that contains all subset. Okay, let's do one quick example. What's the power set of a set containing 1, 2? What's this power set here? Empty set, set containing 1, set containing 2, set containing 1, 2. Okay. Good. Next, we'll define again what's the union. Quickly go over what's the union of two set. Okay, what's this? So this is the set that contains all elements that are either in X or in T. Okay. So as a set membership, way to write it out, I should write X is in S union T if and only if S is in S or S is in T. Sometimes they refer this to the axiom of union. Okay, you could take unions of set. So typically union, what does union do? Union can increase the size of the set. Okay, because although I said, all right, pick one, but if you satisfy one of them, it is in the union. So you could increase the size of the set. For example, I take union of this group, this group. So either if you are on one of the group, you are in the set. Okay, so this is union. And let me see. Okay, so this is just union of two items. We can go further, union more set. So let me write down. So definition. So we can use indexes to label our set, for example. And let's consider collection of set labeled by I. You need to try and get yourself comfortable with this kind of labeling, because when we are doing pure max proof, right, we like to generalize the statement to n, to general and not finite n or specific n. Okay, so we could take the union of all set inside F, or for example, like this. Okay, so what is this? Union of all set in F is, let me write down the set notation here. It's all the elements, okay? We kind of mesh all the elements together. And then this S is in A. Oh. Where am I doing here? I think I put some wrong quantifier there. Okay, there's this some A in F. Okay, either one of them. Or yeah, I do like this. Does it make sense? Does it make sense or not? I mesh everything in the set into another set. Okay, let me show you one example. Maybe let's say I mesh these two together. It will become a set that contains 1, 2, 3, and 4. Okay, so whatever I say, you need to picture with an examples. Then when I say mesh, so what do I mean mesh? Or you see, I mesh the elements from two sets into one set. Okay. Okay, so another example, maybe if we take my indexing set as a natural number, okay, I will sum all the way from 1 to infinity, something like that. Okay, if my indexing set is finite, then the union is just a finite union. Okay, Some prototype of these AI you could think of is like you take some union of open interval inside the real, where you can take arbitrary union, okay, infinitely many union of open interval in real numbers, or you can take finite demand of them. Okay. Okay, good. Next. I will go fairly fast here because it's a bit of recalling of set theory. If it's too fast, you just stop me. Okay, the intersection X intersect S of two sets S and T, okay, is what? Is the set containing all elements that are in both S and T, okay, not just one of them, but both this time. Okay, so we could write it as S is in S and T if and only if S is in S and X is in T. Okay. So one exercise you can do is try to generalize to arbitrary index set, okay, like what we did for the union. Okay, try generalize these definitions to arbitrary intersections with index set. Do you think that this index set makes sense or not? Does it make sense? We need to label, right? So that we know which set we are talking about. We need to label them. Okay, label them 1, 2, 3, or label with some labeling. Okay, index. And if we talk about intersection, we can say that two sets S and T are disjoint. Okay, two sets are disjoint if S intersect T is empty. Okay. If I say two sets are disjoint, meaning if you take their intersection, there's nothing there. Okay, it is disjoint. Okay, so far okay or not? Just definition. Okay. All right. For example, what? For example, what here? So maybe you can give some example. What are the disjoint set you have encountered? Simply take rational number and irrational number. I think I should do it this way. Okay, this is empty. You cannot be rational and irrational at the same time. Okay. Yes.
How about empty set intersect with itself?
Empty set intersect with itself. Let me think. Can we do this or not? Let me see. So you see, S is in the intersection, meaning S is in phi, and then S is in phi. So both sentence is false. False, false, false. So there's nothing in there. So yeah, this is am I doing stupid things or not? Let me think. I think it's correct. So I think it's correct. Logic is correct, right? So if I substitute empty here, right? So talk about an element is in this intersection. I need to talk about X is X in empty and X is empty in empty again. But there's nothing in there. So these two proposition have to be false. Huh? Sorry? What do you mean very closely true?
There's always a thing inside.
Wait.
Inside.
Wait. So you mean there's always a thing inside there?
There's always a thing inside.
No. I mean, wait. Come back again. So false and false, right? Is false. Okay, so this part is false already. Huh? So this part is false. So meaning there's nothing there. So for the whole things to be true, you need false, false. Right? You either true or false, false, true for biconditional. So you have one side false, but you want the whole sentence to be true. So false, false, true. So here have to be false. So there's nothing inside there. Does it make sense? So there's nothing inside the intersection. So if there's nothing inside the intersection, then there's only one set like that. It's the empty set. I think this makes sense. Correct? Correct. Okay. Okay. So any other peculiar example? Okay. So far so good. Okay. Let's introduce some property on intersection and union. Okay. So suppose A, B, C are the set, and we have some index set. So we are trying to generalize properties here. If you saw some indexing set, so what kind of property we have? This intersection and union are symmetric actually from the definition, right? You just stop the order, the proposition doesn't recognize the order. Correct or not? P and Q and P, Q and P should be the same, right? Because we just care about the true value. It's not the order of the proposition. Does it make sense why I said? Okay, everyone follow. Okay, later I'll show you. Later I'll show you. Okay. Next, how about three of them? Okay, so it is associative. You can do this. You can union the last two, or you can union the first two first. And similar to the intersection. So these operations are associative. So first line tells you it is symmetric. Second line tells you it is associative. And then A is a subset of A union B, but A intercept B is a subset of A. It should make sense, right? A intercept B potentially reduce A. Okay, A is a subset of B if and only if A union B is equals to B. Okay, and then A subset of B. Should we have a proper? Maybe not proper. If and only if A intercept B is A. Let me see. Do we need a proper one? We don't need. Okay, let's put it here first, and then we'll prove it, and we'll see how. And the next one, how about putting intersection at the site of union? Okay, so it distribute. Okay, distribute. A intercept B, union A intercept C. And similarly, if you do union on intersection, it also distribute. Okay, where? Something wrong? Let me see. Last second line. What's wrong? Union, intersection, correct? Okay. Okay, so we can generalize the last property here to arbitrary union and arbitrary intersection, where it becomes, if you do intersection on union, it becomes union of intersection. Then if you do union on intersection, it becomes intersection of the union. Okay, let's prove some of them. Let's prove some of them. In particular, I want to talk about this symmetry first. I want to pick up this line here. Proof A union B equals to B union A. Okay, just now I said that our definition of union is blind of order. Okay, what do I mean by that? A union B means what? X is in if and only if X is in A, all right, or X is in B. But How about X in B union A? If and only if X is in B or X is in A. But aren't these two the same? P or Q or Q or P is the same statement. So meaning this proposition doesn't have order problem. So that's why it's symmetric. Okay. Fair enough. You agree? Agree, yeah. Yeah. Sure. So if you want to like you're trying to be pedantic, so how you show these two? So it's like P or Q and Q or P. Then you show that they are the same. Logically equivalent. Is that enough? Yeah. Okay. Similarly for intersection. Okay, similarly for intersection. So for all these property, right, you should show two direction if you see equalities, right? And then any one of them you are interested to show other than the first two? Anything interested to see? Sorry? The index one, is it? No, continue, finish your sentence.
Introduction.
Mm-hmm.
The index type I think it has to be if initialized such as
I mean yeah. The point here is, irregard what kind of index set you put, it is true. Whether or not infinite, it is true. Anything. And it should be anything, right? Should be anything. Yeah. But I think the proof will be different. The proof will be different depend on what index set you have. Why not? Why not? Countable is just 1, 2, 3, 4, 5, 6, 7, 8. Uncountable is like a real number, right? I mean, but real number is the ordered set, right? So you still, but of course you cannot prove by induction in that case. But the point here should be it works, unless you can give an example it doesn't work. I think it should work. I mean, is there anything that it doesn't work? Sorry. Let me think. If you can invest it. Is it? Okay. Let me think. I know. Wait. He's somehow like talking about can we index with uncountable stuff, right?
But I don't think it makes sense.
Makes sense of what?
We use the index to be index set to be R, to be the real number. We set every set like bk to be the number k itself, the set of number k itself. And I think that's an index, but I don't think it makes sense.
You don't think it makes sense?
Yeah, but that can be defined, I think.
Can be defined. Okay, so the question here is whether the index set can be uncountable. Right. Okay. I think can, but let's come back to that question again. Okay, I think can, but I'm not sure, but I can check back again. Okay, so we'll confirm this next time. But other than that, any problem with showing this equality? Do you know what you need to do if you want to show this subset of equalities? You know what to do? Okay, how about the rest? If okay, make sure you can do at least half of it. Half of it. So for the last one, at least you need to show for like what we said just now, countable set. So can you use induction to prove if the index set is n? Okay. Okay. Let me see. Yeah. Let's continue. Any question? Okay. So we will get back to this index set to be uncountable, and then see if there's any issue on proving the last property there. Okay. Next part. So we will define a complement of a set. Okay. So a complement of a subset in particular. So let S be a subset of T. Then the set T slash S or T minus X or S to C is called the complement of X. So what is this complement? I haven't tell you what is it. That is for every S in T slash S, if and only if S is in T, but S is not in S. Okay. Okay, so you will expect some De Morgan's law here. Okay, let A B and AI again. So maybe there's a potential problems on the uncountable. We will check it again, but we will have A union B taking complement is the same as taking complement of A and B first, and then taking the intersection. Okay, it's like the De Morgan's law. And similarly, if you take complement of an intersection, you will get complement of a union. Okay, so you can try and generalize this, put more and more union inside the complement or intersection inside the complement. Yes. You need a universal set. Yeah, sure. Depend on your universal set. Yeah. Yeah. So you mean universal set that contain all of these, right? Yeah. Yeah. That's right. That's right. Yeah. That one is implied. It's implied. Yeah. That's right. Because you know why? We could change the universal set because A could be in U1, I could be in U2 as well. So we can change the universal set. So it depends. I mean, okay, it doesn't depend actually. I mean, yeah. So you can create any universal set you like. Okay. Yeah, it doesn't depend on universal set that. It doesn't depend on the ambient set it lies in. This is what I want to say. Okay. But to define a complement, definitely you need a universal set for them. Does it make sense? Okay. Okay, so these are just a set equality, so you should use a definition and then pull out your proposition logic to prove it. Okay. Okay, before we end, right, let's introduce last piece of definition here. So let's define an ordered pair. So for now, we only introduce set language, right? So we need to define order pair as a set. Okay, so what is this set? So this is a set that contains a set containing S and a set containing ST. And this will do us good job. What's the good job we want here? So if two ordered pairs are the same, if and only if x1 equals to x2 and t1 equals to t. This follows the equation, right? x1, y1 equals to s2, y2 if x1 equals to s2, y1 equals to y2. But using this definition to show it. Why this form? Okay, so this actually is a defining property for our ordered pairs. And we just come up with one construction that it works. Potentially, you can come up with different construction, like how we construct empty set just now. We can construct empty set in various ways. But in this world, there's only one thing that do the job. I mean, there's only one real empty set, right? So we can define differently, but this is the defining relation we want, or property we want for ordered pairs. Yes.
Why the definition include the second component include SMT?
Yes, purposely. Yeah. So you will use this in this proof. Okay, so I will left this as an exercise and then I will prove it in the next section. Okay, you try and prove it using this definition, and then I will resume next class with this proof. Okay, and for all these exercises or this content, right, you should find in the, where do you find? Moncrief, Richmond, or Proctor notes, or John Hutchinson note. Okay, these four references you should read. And these four references where I get these materials. I will combine and mix. And my lecture note will detect what is important in my course, and then what will be tested, what I wanted you to know from my class. Okay? Okay, so see you tomorrow. We'll resume with this group.怎么的？几点？哦，MPU。哦，OK。OK，拜。拜拜。Yeah.
Question.
Yes.
I think this song. Before I read the book, it's written by Bourbaki.
Yeah. Because Bourbaki.
Element mathematics.
Sure. I know
Then he says he says the same construction.
Okay, he said the same conclusion. Yeah.
Sure. But then he say that
Sorry. Then we should go. Yeah.